So welcome everybody to this VSA online webinar, and I would like to welcome Mike Heddes. So sorry for misspelling in the announcement your name, but so today so Mike has already presented Torch HD during this season of VSA Online. So today he will present his research contribution. So Mike, the floor is yours, please.
Thank you. You see my slides now?
Yes, I see your slide.
All right, thank you. Yeah, I'll talk today about how do we represent circular data in HDC and VSA, and I'll describe two applications where we use this this representation that we introduced. So an overview of the presentation. I'll very briefly talk about HDC because I suspect most people will be familiar with that here in the audience. Then I'll talk about how the method of representing circular data that we propose, and then two applications. We use them in a dynamic hash table, and we use them in a learning setting where it can be a useful bias if you know that some of the data has a circular property to it. And we'll talk about exactly what that means later. So just a one-slide overview of HDC. So in HDC, one of the important properties or components of an application is how do I map my information and represent it in this high-dimensional space, which I denote here with the encoding phi. So we go from some input space to some high-dimensional space. And this encoding determines to a large part the behavior of your system, and lots of papers propose different modifications to encoding functions that are specific for some application and work well for that application they care about. So then when we're in this high dimensional space, we have approximately 10,000 dimensions, and in this presentation I'll just assume the binary hyperspace for simplicity, but most of the things I talk about will apply to the more general hyperspaces, bipolar or complex hyperspaces. Some important thing to note is that the information in these hyperspaces is represented holographically, meaning that none of the elements themselves contain necessarily any information. It's the pattern of the bits that contains the information. And in order to make inferences or to make some conclusions, we look at the similarity between hypervectors, where high similarity tells us one thing and then low similarity between hypervectors tells us something else. Then we have three operations on these hypervectors. The first one is binding, which is used to associate information. Can be useful to create, like, let's say, a dictionary of key value pairs. Then we have bundling to aggregate information, and permutation to assign some sort of order or preserve order of information. And these can be implemented as simple multiplication or XOR, summation or majority gate, and permutation of elements of the vector. All right, so nothing too crazy here for most of the people in the audience. Then I talked about how the encoding is an important aspect. So the very most basic way of encoding information is to represent symbols, for instance, the alphabet, as random hypervectors typically. And they are created just by generating or sampling a random point from this hyperspace. So in the binary case, random ones and zeros. And the interesting property here is that they're all expected to be orthogonal, and they're quasi-orthogonal with very high probability if you have a large enough space. And this means that if you look at the plot on the right, where I plot the pairwise similarity between all the hypervectors in a set, in this case a set of 10, then they'll all be quasi-orthogonal to each other, except the diagonal, which is the same. You're similar to yourself, obviously. Yeah, so this can be very useful for encoding symbols such as the alphabet or something. But what if you actually want to capture some similarity between items? For instance, if you want to encode an interval where, let's say, you want to encode the interval between 0 and 10, then intuitively, at least to us, 0 and 10 are less similar to each other than 0 and 1. So numbers that are nearby are, at least to some intuitive sense, more similar than numbers that are far away. And we can capture this using level hypervectors. So you can create some discrete set of hypervectors. We denote them here as L. And again, on the right, I plot their pairwise similarity. So if we look at the starting point of the intersect or the interval 0 to the end point of the interval 9, we see that the similarity between the levels decreases linearly as you go from one end to the other end of the interval. And we create this by interpolating between two random hypervectors that represent the endpoints of the interval. And in our work, we provide an algorithm to create this, which I believe is a little different from other works that I've seen out there that also use level hypervectors. In that, in our case, in some of the other works, I saw that there is either a fixed number of bits that are being flipped, or the endpoint is exactly orthogonal to the starting point. Whereas with our method, the endpoints are quasi-orthogonal because they're both randomly sampled, which in expectation still is the same thing, but now opens up many more pairs of intervals to be created, which gives you a higher information content because the probability of seeing any one is lower. And we do this again by sampling two random hypervectors for this endpoints, so L1 and Ln in this case. And then what we do differently is that we also sample we call it a filter vector, which contains random numbers between 0 and 1, or some random integer would also work. Then for all the levels in between, we set some threshold value tau, which is dependent or calculated as the linear interpolation value, which goes from close to 0 to close to 1. And then for each dimension, we either sample or either select the element from L1 or Lm, depending on whether the filter value is lower or greater than the threshold value. So what this does is, in the earlier levels, when the threshold value is close to 0, you will select many more of L1, and whereas in the later levels, when the threshold value is close to 1, you'll sample many more of L. And this, in expectation, achieves exactly the linear similarity interpolation between L1 and Lm. So this is how we propose to create level hypervectors. And then the one question that remains is, how do you represent circular data then? Because intuitively, let's say you would use, let's go back to the level ones. Let's say you would use the level hypervectors to represent a circle. So I start at 0, and then I walk along the circle. And at 5, I am at the other side, opposite side of the circle. But this point, the hypervector that I have here, is only half similar to the original point. Or I should say it's still half similar to the original point, even though this is the furthest away on the circle you can ever be, right? The opposite side of the circle is the furthest you can be from your starting point. And if you would walk in any direction from there, you would actually get closer to your starting point. So intuitively, it makes sense for the opposite side of the circle to be the orthogonal point. Whereas with a level hypervector set, if you would continue your circle, one step before you get back to your original point, you're the most distant if you would look at your similarity profile, which doesn't exactly match our intuition of what a circle would be like. So to fix this, we introduced the circular hypervector sets, and they do capture this correlation profile, such that if you are halfway along the circle, So you're at location 5. This point is now quasi-orthogonal to your starting point. No matter where you on the circle you started, always the opposite side is quasi-orthogonal. And then as you keep walking, you actually get closer again to your original point in either direction of the circle. And this can be very useful to represent angles or directions that also capture or follow this correlation profile. So the way we create these is based upon the level hypervectors that I mentioned 2 slides ago, and they make up the first half of the circle. So here in the top of my plot, I am just creating level hypervectors. So C1 to Cn/2 is one set of level hypervectors, where C1 and Cn/2 are randomly sampled. And the thing that I now denote explicitly is the transformations in between them. So between C1 and C2, there's some transformation. So in the binary case, some bits that are flipped to go from C1 to C2. And I store these transformations in a queue during my forward pass. That creates the first half. Then when I want to create the second half, what I do is I apply the inverse transformations, which is again just binding with the same hypervector, because in the binary case, inverse is the same as the normal binding. But in the complex case, this would be taking the conjugate. And by applying the inverse transformation here to the end point, so this was the second orthogonal point, Cn/2, I now apply this inverse transformation. I am getting closer to C1 because I removed this transformation that got us from C1 to Cn/2. But I'm from the perspective of Cn/2, I'm still moving further away because I'm applying some transformation to it. And for the same goes for all the level hypervectors between Cn/2 and C2. All of these level hypervectors are getting further away from after I apply this transformation. Only C1 is getting closer. So now C2 is quasi-orthogonal to Cn/2 plus 1. And this process continues till I complete the second half of the circle. So I'm always applying the inverse transformation in the order that I did the transformations on the forward pass, which will get me closer to the original point. But still in each half of the circle, there's enough transformations to make them distinct transformations, I should say, to make them quasi-orthogonal to each other. And so the use of a queue here is key, because if you would use a stack, obviously you would get the exact same hypervectors in the forward pass as in the backward pass, because you would just undo them in the same order as you did them. So at this point, maybe it's a good point to ask some questions if they're there.
I have maybe one question about parameterization. So the number of steps you do to encode a circle. So it depends on the size of the circle, right? So the number of levels you want to have. So how do you compute the number of levels?
So it's easier to start with an even number of levels. And then if you want an odd one, you can just remove almost half of them. Then you have an odd number. So let's say you want 10 levels in the full circle. You would make 1 or 0 to 5 level hypervectors. And then the remaining ones you can create from the transformations between the level hypervectors.
Oh, okay, I got it. Mm-hmm.
I might be one off in the discrete math there, but yeah, that's kind of it. If there's no other questions, then I'll continue. So with this, we now have 3 types of sets of hypervectors. The random one, the most simple, no correlation between any of the information. Then the level one, which has a linear correlation of information, or can represent an interval, the real number line. And then the circular hypervectors, which can be used to encode, let's say, a continuous interval, such as 0 to 2 pi, for instance. Then I'll now go into the applications that we do that using these circular hypervectors. The first one is the dynamic hash table, which is a system that tries to map requests to, let's say, a dynamic cluster of servers, as one example. And this happens a lot in load balancers or even peer-to-peer networks. And the problem that arises in this application is that if you would use a naive way of mapping requests to servers, so let's say you take the hash of the request mod the number of servers, then every time the number of servers changes, you would be redistributing the requests to different servers. And this at face value doesn't seem so bad because you would still assign, if your hash function is good, then you would still uniformly assign requests to servers. But if you would, if a request can go to the same server, you could do optimizations in cache hits, such that if a user is interacting with a server multiple times, its information can be cached on that server, and therefore you have to do less trips to the database and reduce the load on that server. But if you redistribute all the requests over all the servers, now you have a lot of cache misses, and therefore your load on the servers increases. And to cope with this, there's two main algorithms that are used right now. The first one is consistent hashing, which is used by AWS and Google Cloud Platform, that maps both the servers and the requests to a unit circle, and then assigns the requests to the next server on the unit circle. And this can be done in log n time by using a binary search tree. Then there is rendezvous hashing, which is also called highest random weight hashing, that assigns this request to the server that happens to get the highest hash value. So what you do is you hash each request with all of the servers in the cluster, and the value that comes out of this hash that is the highest will be assigned to that server that happened to get the highest value. And again, if your hash function is good, then this should also give a uniform assignment of requests to servers, and it will minimize redistributions. With one disadvantage that now it's in O of n, because you have to do all these hash functions calls, n of them. So these are the existing methods. So why do we need HEC to play a role in this setup? Well, that's because, as I will show in the results, these methods actually degrade in their performance when we consider them in a noisy environment. And with noise, I mean memory upsets or bit flips in the memory. And there's been research that showed that Google's machines, actually a third of them experience memory upsets or bit flips each year. And there's been separate research that shows that as the feature sizes of the memories are shrinking, that multi-cell memory upsets, so events where multiple bits are flipped at once, are becoming more common, and they're accounting for 45% of the memory upsets. So this could really, for some critical applications, maybe cause some safety concerns, or could cause the servers to go down if the uniformity of assigning requests to servers is affected, or if the load all of a sudden is increased because of redistributing, especially in scales of like Google and stuff. So maybe there's room for an alternative solution that we propose that is more robust, and that is done by translating the problem to an associative memory lookup using these circular hypervectors. So a small recap of what is an associative memory for the ones that are not so familiar, although I think most of them all are. So we take a simple associative memory where we return the value at the memory address that is the closest in Hamming distance to the query. So you have some memory keys, K, some values V, a query Q, and then we return the lookup result VI, where I is the argmin of the Hamming distance between the keys K and the input query Q. And there's been work that showed that this can be done very efficiently using FPGAs in a single clock cycle by taking advantage of the parallelization of all these operations. And something to note is that this is equivalent to the cleanup memory if the keys and values are identical. All right, so that being said about the associative memory. So what we use that in our hyperdimensional system, hashing system, to represent the circle on the right, which is all the circular hypervectors set that we create. So you specify some m number of these hypervectors that represent the circle, and then we assign servers randomly to one of the nodes on the circle, so to a random hypervector. And we also assign each request R randomly to a hypervector on the circle. And we want to assign the request to the closest server on the circle. And since the hypervectors are circular hypervectors, closeness on the circle is captured by the similarity of the hypervectors. So such that we can use the associative memory to return to us the server that is the closest on the circle using associative memory. And obviously the random assignment is done deterministically using some hash function such that incoming requests will go to the same server if the server is still the closest in the next step. So this is the basic setup of our hashing system. And I will now talk about some results that we got. So maybe not very surprising to most of the audience here, but because of the high redundancy of HD, we had no mismatches, even up to 10-bit errors. Whereas the other methods did suffer quite significantly from the bit errors. And even though 10-bit errors is maybe quite rare, some of the papers do actually mention that they do happen, but obviously fewer bit errors are more common. But still there for consistent hashing, there can be quite a significant number of mismatches between requests and servers. So you could see the percentage in mismatches as the increase in server cache misses that you would have in your system. So then the question is, okay, what do we give in for this or give up for this improvement in robustness? So if we look at the efficiency, we see that the consistent hashing is the most efficient because of its log n complexity, and rendezvous hashing has its linear time complexity. So we here look at the time it took to handle a request and the number of servers in the cluster on the x-axis. And we see that HD hashing is actually very similar in complexity, or at least in this timing plot, to consistent hashing, because it can utilize the parallel operations very well. And maybe more importantly, if we look at the uniformity of the distribution of requests to servers, which we measure using the C-squared error, where lower is more uniform, we see that HD hashing, even at 0-bit flips, is more uniform than consistent hashing, which is the same color but a dotted dashed line. And more interestingly, when bit errors occur, the consistent hashing actually starts being less uniformly distributed, which means that there's some sort of compounding process of not only having, let's say, 5% mismatches, but those 5% mismatches are now also more concentrated on some of the servers because it is less uniformly assigned, which is kind of a compounding, because not only do you have increased cache misses because of the redistribution, but also you have higher load in general because of the non-uniformity, which could make increase the chance of a server collapsing. And we see no such evidence or behavior with HD hashing in this setup. All right, that concludes the first application of the dynamic hash table. Then I'll ask if there's any questions about that. If not, we can also get to it at the end. Then I'll keep going with the learning setup or learning application. So for this, we use a very simple standard training setup where we specify some encoder for each application. And then we train for each class a model simply by bundling all the hypervectors of that class. So it's a centroid encoding or training algorithm. And then during test time, we use the same encoder to create a query vector and then return the class that has the highest similarity. For regression, we do a little bit different. We have only one model, which captures both the XY value pairs of your regression setup. So where X is your input values encoded, we bind this with the Y value, and this becomes your model by summing up these XY. It's basically a hash table of XY pairs. Then to get a prediction, you query this hash table with a X, which will give you back an approximate Y. You can decode this Y to get your regression result. And when we use this setup and only change the type of hypervector that we use, we see the following results, where for the Beijing data set, we are trying to predict the temperature in Beijing over a given year. And we use the circular hypervectors to denote the time of the year. And since the temperature fall is a very periodic signal, which is cyclic throughout the year, so cold in the winter and then some sinus the temperature goes up in the summer. By adding a bias that captures this period, using the circular hypervectors, we get a significant improvement in the mean squared error of predicting the temperature. So in this case, we can see that adding that bias does help significantly. And a similar story for the Mars Express data set, which captures the power level of the Mars Express satellite that is in an orbit around Mars. And also there, the periodic distance to the sun is related to the power level of the battery. So that capturing this period of its orbit does help as a useful bias to predicting its power level. Then we also have 3 classification tasks, where the data set is of a surgeon that operates a robot arm, and it's performing a task, such as the three tasks that are specified here: knot tying, needle passing, or suturing. And each of these tasks is divided in a number of sub-steps. And the classification task here is to predict which sub-step the robot is currently performing, given some angles of the robotic arm joints. And by encoding these angles as circular hypervectors, we also see an improvement in the accuracy there compared to the random and level hypervector encodings. Then we have one more topic that we discussed in the paper, which is about hyperparameter, the R value of the circular and level hypervector sets, which can be used to interpolate the set between let's say the vanilla set as I've been describing it thus far, and the random hypervector set. So in the picture on the bottom, when R is set to 0, we have exactly what I've been describing thus far. At the opposite side of the circle is your orthogonal point. And as you walk along the circle, you'll get closer to your original point. And then when R is 1, all other hypervectors are completely dissimilar to each other. which is the random hypervector set. But for some value in between 0 or 1, you can see this basically as trying to adaptively change, let's say, the sphere of influence or your direct neighborhood that has some correlation with your starting point yourself, such that if you have 0.5, the other side of the other half of the circle has no correlation with you, so they're completely dissimilar, but your direct neighborhood still has some correlation with you, such that if you increase from 0.5, this would shrink, and if you would increase it from 0 or decrease it from 0.5 to 0, this would increase to become r equals 0. So you can therefore dynamically or set let's say the influence along the circle that each point has. And why this might be useful is intuitively because if you only have 2 orthogonal points and all of the information is some combination of these 2 points, all your predictions on your classification tasks. Whereas if you have all orthogonal points, you can store a lot of information, but there's no way to figure out how to relate or interpolate between any of these values. So when r is 0, you're very good at interpolating between values, but you're not able to store as much information. Whereas with r1, you're able to store a lot of information, but there's no way to interpolate. So any r in between can let you trade off how much do I want to interpolate and how much information do I want to store. This is the high-level, more intuitive explanation for what this r value does. The exact details of how this is accomplished you can find in the paper if you're interested. But I think for the presentation, it's more important to give some high-level intuition. So then how does this r value affect your accuracy in a classification task? So here we plot the normalized error, where we are normalizing against the usage of the random hypervectors. And we see that if you would only use r equals 0, so the vanilla set that we've been using throughout the presentation, or r1, which is the random hypervector set, you would in none of the situations get the optimal result. Whereas if you had r slightly higher than 0, but still very low, you get, in some cases, there's very significant improvement in error, and some cases slightly less, but still an improvement throughout all of the setups that we tried, which gives some insight that increasing the information that can be represented is helpful to give up some of the interpolation abilities. But these are only some preliminary results. We're not exactly sure what exactly is happening here behind the scenes, but these are some results to highlight that there might be some more research to be done in this area of figuring it out, and that it is useful to have some parameter like this. Yeah. Then we get already to the end of the presentation. I'll conclude with listing some of the contributions, which is that we have introduced the circular hypervectors that allow you to capture the continuous interval, the correlation of that profile. Then we use this to do a dynamic hash table, which is more robust with similar efficiency. And at last, I've talked about how to use the circular hypervectors also in a learning domain. If you have some prior knowledge about the information that you're encoding, if you know that they are circular, then it might help to use the circular hypervectors to encode them. And lastly, I mentioned the R value, which can be used to trade off either data representation power or interpolation power of your hypervector set. And with that, I want to conclude the presentation, and I'll take any questions if they're there.
Thank you, Mike. So now I open the floor for questions. Let me see. Well, maybe I can start with the command, not a question, but rather a command for your information. If you work with this the application is interesting. I mean, about this hash table, it's kind of straightforward on the one hand, and on the other hand, it's kind of useful in real world. But my commentary is about the way to generate circular hypervectors. So you there is one way to do so. I mean, a rather straightforward way with HRRs or FHRRs, which was, I think, presented in paper by Fritz, Paxson, and Dennis. So basically, the way how you generate the so it is used this fractional power encoding, and so connected to selecting a distribution of phases. I mean, for initial vectors, and for some distributions, like I mean, more deterministic distributions of angles. So these FPEs, they create so-called periodic kernels. So they basically which possess this periodicity property. And so maybe you can find it useful in your other applications as well. So because it's not only like one-dimensional circle, so you can have as many dimensions in FPE as you want.
Right.
So that was my commentary.
No, that's indeed also can be very useful. I do believe there's some differences in that. I think those could only be used if you have the complex hypervectors, as far as I am aware.
No, no, I mean you can start with the generating phases, but I mean then you can convert to real numbers. So it's not binary, but it's real numbers. So
Right.
HRR vectors, and they could be of smaller dimensionality, that which also, I mean, it's a trade-off. So you don't need like 10,000 dimensions for kind of robust operation. Maybe, I mean, 100 would be enough. 100 of real valued vectors would be enough.
Right. I see. Yeah, that could be useful to look into to see what's the trade-off there between the two
yeah, because there you don't need a procedure. You just generate, I mean, a procedure for creating the entire set of vectors. Moreover, there is also a fast way of navigating through this structure using resonator network. So you don't need to keep all the vectors in associative memory somehow. So yeah, maybe, I mean, I'm thinking maybe this would be useful. If you continue with these applications, maybe this could be useful.
Right. No, I'll keep that in mind for sure. Thank you.
Hey, Mike, thanks for the presentation. Interesting stuff. So I have one question about your motivation at the beginning seemed to be you're talking about the presence of bit errors in computers, and this would provide a more robust hashing mechanism. But I would have thought in the presence of a large number of bit errors, the efficiency of the hashing would be the least of the problems that you would have. So just wondering if I'm missing something there.
So it's maybe there was a slight miscommunication on my part there. I am not necessarily saying there's going to be a lot of bit errors continuously. I'm more saying in the, let's say, the inevitable case that a bit errors occur, you would not want them to affect your system in such a detrimental way that your system goes down if you can help it. So you would still want, for the 90% of the time where there's no bit errors and your system is running fine, you still want the efficiency. But then for the time where you do happen to have these bit errors, which are rare, but they do happen, you don't want your system to completely crash. Does that help in the motivation aspect, or?
Well, yeah, I mean, what I'm thinking is that if you're having bit errors, it's basically gonna just crash any conventional, C++ code, for example. It's gonna, it'll just crash. And if it happened to be, if you got that bit error in, like, the likelihood of that happening during when you were computing a hash value, that would be extremely low.
Right, during your hash value, that is indeed very low. But I think it's more now in storing which. So even with these other methods, at least for the consistent hashing, you're storing the values of these servers and servers only on the unit circle. So you have to store its location somehow in memory, and these could get corrupted. Whereas, yeah, if you have rendezvous hashing, for instance, the chance of it getting a memory upset while you're recomputing these hash values is extremely small. Yes, I agree there.
Okay, but thanks.
Yeah.
Mike, I'd like to say that it's very nice work, nice paper.
Thank you.
Are you familiar with locality-sensitive hashing?
To some abstract level, yes. Not very in-depth, but yeah.
There's been some activity in there, and it works out that LSH is at the core of search machines, and has been for, I guess, since the beginning of DEX search engine. Have you given any thoughts of application to that particular area?
In the search, we do have a paper that is currently under review that is not necessarily search, but it is in the link prediction area, where we also touch up a lot of these locality sensitive hashing mechanisms, and min hash, I believe, is also in this family of hashing, where we do compare with those in order to find the similarities between nodes in a graph. So that's where we touch upon this a little bit, but I haven't more specifically looked in the search yet.
The reason I mention this is that there seems to be an application where placing randomness together with similarity is quite an interesting thing to look at. And it seems that this is conjecture at this point, but that randomness aggregates with additional similarity clusters, if you will. And we're not sure why, but it's a thought for you to maybe carry.
And were you thinking about search in general, or did you have any specific subdomains of search in mind, like document queries or something?
We're working on doing things with in the stock index, and we're quite surprised at what's happening with clustering and the idea of symmetry. We looked at LSH, and it works, but not as well as does as hyperdimensional computing, if you will, HD. Yeah, it's very strange, and I'm not sure why. So we're still in conjecture mode max right now.
Mm-hmm.
That's just something I thought I'd I'll let you know.
Yeah, thank you for your comment.
Thank you again.
Hi, Mike. Thanks for the talk. Very enjoyable. This is this is one of those dreadful. This is more of a comment things, and unfortunately, I'm going to need to explain a bit for the benefit of the audience. This is follows from some conversations we've had in the past. So, as everybody else probably is aware, Mike is one of the developers of the Torch HD Python framework for doing hyperdimensional computing. And relatively recently, I was in touch with Mike and was nagging him and his co-workers to put some features into Torch HD. And one of the things that they've put in is a bundling method that I've called rand cell, and it's probably just a reinvention of the wheel anyway. But I think that we had a conversation, Mike and I, where he was asking, well, what could it be useful for? And I said, I didn't think it was actually remarkably useful. It might be from a direct point of view, but it might be useful for understanding, to just as a way of understanding what things are doing. And in looking at Mike's explanation then of how he's implemented the circular vectors, I think he's actually, the heart of that mechanism is actually using this rand cell bundling. And so the way that the rand cell works is that if you're bundling two vectors, A and B, if you just basically on an element-wise basis choose at random the element from either vector A or vector B. So you're basically hybridizing the two vectors. And if you want to do a weighted bundle, you just have the probability of selection being proportional to the weight. So you're selecting from A with probability 0.1 and B with probability 0.9. So essentially, what's happening, if I haven't misunderstood it, in that in the center of that construction process, is you're taking two vectors and you're doing a rand cell, a weighted bundle of two vectors. Yeah, you're getting there.
Yes.
Yep.
Sure.
Yeah. So this is down that bottom there, that if I strange Greek symbol, etc. That one there.
Yes.
Yeah.
The dimension.
And so I think, I mean, in the past, when I've been doing encodings, if you're just doing sort of a linear interpolation between A and B, you just take the two endpoints and you basically do weighted bundles of them with the weightings reflecting how far along the continuum you are between A and B. Whereas I think what you're doing here is you start off with two endpoints, which represent points opposite each other on the circle. And then you generate one point which is pretty close to your starting point, and then you use that new point as the next endpoint relative to the other side of the circle, and you keep going there. So rather than just sort of being a straight line between A and B, you're effectively doing a bit more of a random walk, and sort of you've got more freedom to, I think intuitively, wander off away from the straight line before inevitably you're then pulled back in towards the endpoint, because you're just getting a higher and higher proportion of weight relative to that endpoint.
That is not entirely what is happening. You always use the L1 and LM. You don't use the M-1. Yeah. So it's always here L1 and LM that you take your elements from. I think the one difference with rand cell is that with rand cell, I believe at each step you would randomly select with some probability. Whereas here I have let's say the thresholds from at which point I get L1 or LM is hard coded by this tau value. And that only depends on this one-time random sample phi. Whereas with rand cell, you would do multiple random selections. I think that's a slight nuance difference.
That's interesting then, because it'd be interesting to see what difference it would make. So that that raises a number of questions. Because I thought that in one of your papers, I remembered hearing you making some sort of point that some particular way of encoding things was getting you better results, and I think the explanation you were advancing was because you're effectively injecting more randomness into the representation, and you were saying that effectively that was more information available to be exploited. But yeah, it'd be interesting then to see if there was any particular difference between this sort of strictly predetermined one-off sampling versus having a more random path between the two endpoints, and a bunch of other things too. So, for example, at the moment, you're saying that basically you've got your transformations going from one side to the other side of the circle, and then you basically replay the inverses to get you back. Does that induce some sort of extra relationship between the two sides of the circle? In that, you know, the second half, if you like, is sort of the exact reverse of the of the first half. I mean, so if you were to go from A to B, and then completely independently go from B back to A without replaying, so just use the same process, you got to A to B to go back from B to A, but with a different random sampling, would that produce an encoding which was different in some way from the way that you're doing it, which is sort of much more constrained?
Right. Maybe in that way you could inject more randomness to the process.
Yeah.
Yes.
Yeah. And then the other point I think is picking up on a point that Evgeny made, which is I was just looking through your HD Torch documentation yesterday, and it seemed to me that with these encodings, that if you had some inherently continuous value, let's say the level encoding, but the same thing applies to the circular one. If you had some inherently continuous value, it gives the impression that you first map to the discrete value which is present in your code book. So you do your code book generation first, and then say, well, if I've got this continuous value, I'll map it first to the closest discrete value before that's in the code book, before I then go and use the hyperdimensional representation. So I think that, and this is getting back to Evgeny's point, that, you know, with the fractional power encoding, you can just as a one-off mathematical step go straight to some arbitrary value that is at some level which is not directly in your code book. So in terms of encoding, I don't know, robotic inputs or something other like that, it might be advantageous. I mean, obviously, if you've got a fine enough set of pre-existing values in your code book, it's, you know, you get to a point where it's not going to do you any harm, but it might be interesting to see whether you could get one-step versions of what you're proposing here.
Right. I've been thinking along these lines also, and I think that would be possible because you only have to store 3 hypervectors, so L1, LM, and then your filter vector. And then from there, you could generate any one in between to any arbitrary precision, given that it's less than the number of dimensions, obviously, because that's then your constraining factor.
Okay.
So I think we will add this to the library at some point, because that would be, I would add an improvement.
Yeah,
I think.
Okay, terrific. Thank you very much for that.
Yeah, you're welcome.
Any more comments? Questions? Well, if not, then I would like to thank Mike again for the great talk and the generated discussion. So thank you very much all for attending. And next time we meet 19th of December. So same time, 8 p.m. GMT. And we have an open discussion about work in progress / challenges in VSA HDC. So
sorry again for keeping everyone waiting.
No worries. But thanks for coming. And so thank you all. So see you next time. Goodbye.
Bye-bye.
Goodbye.